Everybody, Dr. A here, and in this video we're going to be exploring an example of allowable stress. So let's go ahead and get started. In the given information, we're being told that the bolt is made of a material having a failure shear stress of 80 megapascals, and we're being asked to determine the maximum required diameter of the bolt using a factor of safety of 3 against shear failure. And in our diagram here, we have a fixed connection on the left where we have one plate fixed to a wall, and then that plate is bolted to a second plate that is supporting a 100 kilonewton force, okay? So since this is really a shear stress type of problem, the first thing we need to ask ourselves is what kind of shear is that bolt experiencing? Is it single shear, double shear, or so on? So the answer is single shear, okay? Why is this subject to single shear? Well, it's because there is one shear plane, and so there's only one plane that bolt could experience a slicing effect. All right, and so since there's only one shear plane, i.e. single shear, the shear force through the bolt is going to be the full 100 kilonewtons, okay? The next thing we want to recognize is our relationship between factor of safety and a failure stress and an allowable stress. So using shear stress, we're going to say factor of safety equals tau fail over tau allow, okay? Now, do we have some of these values so far? Yeah, absolutely. We know what the factor of safety is. It's 3. That was given to us. And we know what tau failure is. That was given to us up here. Failure shear stress of 80 megapascals, okay? So this is one relationship we have. We also know that the allowable shear stress is going to be related by saying shear force divided by cross-section area. Okay, now do we know any of this? Well, kind of, yeah, we know V. V is that 100 kilonewtons. We also know that cross-section area is pi d squared over 4. Why do we need to use that? Well, the problem asks for the minimum required diameter of the bolt. So the diameter of the bolt comes from the area of the bolt, which is this relationship here. So what we're going to do is we're going to substitute these 3 different relationships into each other or set them equal to each other as appropriately to finally solve for D. So let's try to do this without substituting in values first, because if we can do this algebraically, then we're going to show that we can do this no matter what the numerical values actually are, okay? So the first thing I'm going to do is I'm going to take this first relationship and I'm going to solve for tau allow, okay? Tau allow is just going to be tau fail over factor of safety, right? Just cross multiply these two with each other, all right? Now, tau allow is tau fail over factor of safety, and tau allow is also V over A. So what can I do? I can set these two expressions equal to one another, right? So I'll go ahead and do that. I'm going to say tau fail over factor of safety is equal to V over A, all right? Now, what can I do? Well, ultimately, I need this diameter here, which is inside of A. So how about I do some rearranging and I solve for A here. Solve for A in this relationship. So if I just do a little bit of rearranging and solve for A, I'm going to get V times the factor of safety over tau fail, okay? How did I do that? Well, again, I just cross-multiplied this up to the left side of the equation. I cross-multiplied this fraction down here, and I flipped the fraction, okay? Now, what do? Well, we know that A and A are the same thing, so that means I can set V times Vs over tau fail equal to pi d squared over 4, right? So I'm going to say V times Fs over tau fail equals pi d squared over 4. All right? Now what do? Well, I finally just solve for the diameter here. And so I can do that by saying diameter equals the square root of 4 times V times the factor of safety divided by pi times tau fail. Now, what I have here is a nice little compact closed form solution where all I've got to do is substitute in my values for V, factor of safety, pi, of course, and tau fail, and I'll be able to calculate that diameter directly. Now, could I have just started substituting in numbers up here? Yeah, absolutely. I could have started substituting in numerical values early on in the solution, and that would be fine as long as you manage your constants and your algebra correctly. You'll get the same answer compared to doing this more, algebraically or analytically like I did. I prefer doing it this way. I prefer doing all my algebra before I start substituting in values because it's easy to combine and lose track of values if you start substituting them in too early. And again, as I already said, if you can solve a problem in its most generic form, then you'll be able to solve that same kind of problem no matter what constants you have. So let's go ahead and solve for that diameter. So it's going to be square root of, draw a better square root. So 4 times 100 kilonewtons times a factor of safety of 3 divided by pi. Now what's tau fail? Well, tau fail, again, that was given to us in the problem statement. Failure shear stress of 80 megapascals. So we got to watch our units because notice we have kilonewtons as our shear force. So instead of 80 megapascals, I'm going to take this to 80,000 kilopascals, okay? And then I'm just going to clean this up a little bit so it looks a little more organized. And I'm going to punch this through, and we're going to see what we get. So do this with your calculator with me. 4 times 100 times 3 divided by pi. And then also in that denominator, 80,000 kilopascals. And then we're going to take the square root of that, okay? Now, I get 0.0691. Now, what are the units here? Let's think about that. What are the units? Well, it should be units of length, right? Because you're looking for a diameter. Now, this pops out in units of meters. How do I know that? Okay, let's ask ourselves that. How do we know that that's units of meters? Well, let's look at our units that are inside of the square root. We have 100 kilonewtons, and then we have 80,000 kilopascals. So I'm going to make a little note here. I'm going to say unit check, okay? And so here I'm going to have kilonewtons divided by kilonewtons per meter squared, and all that's inside of a square root, okay? So I'm forgetting about all the constants for now. I'm just checking my units on this kilonewtons and kilopascals. Remember, a kilopascal is a kilonewton per meter squared. So if I do some rearranging here, what happens? Well, the kilonewtons cancel, the meters come to the top, so you're left with meters squared inside of a square root, which just leaves you with meters. So the units check out, okay? So you can leave this answer like this, but it would probably make more sense since we're dealing with a bolt to convert this to millimeters, okay? So I'm going to convert this by moving the decimal 1, 2, 3 spots. So this will be 69.1 millimeters, okay? So that's the final answer. Now, in reality, you would probably round this to a reasonable number. If you were to round this, you would probably round to 70 millimeters. So we'll make a note here, round to 70 millimeters. The reason why you would round up and not down is because, remember, the 69.1 millimeters, it's fine. It's got that factor of safety of 3 in there, but 69 millimeters is kind of a weird number, so you would probably round it to 70 or 75 millimeters, especially if you're selecting a bolt that's prefabricated. Most bolts don't come custom diameter. You have to order them within a certain diameter that it's produced in or manufactured in. So So you'd probably look at 70 or 75 millimeter diameter bolts, whatever the manufacturer has available. Okay, so that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other things like this. Thanks for watching.